So welcome to lecture number 41 of the Statistical Thermodynamics course. So as we saw that we have been able to establish that what are the translational modes and for a monoatomic gas. So we already wrote the definition of pressure. Now we are going to look at the entropy. For entropy, okay, for the translational component of entropy, it's 3/2. We just use the transfer function, not the partition function definition for entropy, plus ln e over n plus 2. Okay, so if you substitute PV equal to nkt, capital N. Okay. We get S by R, this is small s, remember, is translational, equal to ln 2 pi m 3/2 kt 5/2 h cube e plus 5/2. Okay, this particular equation can be converted to the form we write next. Okay, if we do the evaluation properly, T so T is in Kelvin. M is the molecular weight. Given in kg per kilomole. Okay. P is the pressure. In bars. So it only holds, this equation only holds in the dilute limit. In the dilute limit. And is not appropriate when the temperature approaches absolute zero. Okay, so this is the form that we see. Okay, now let's do a very simple problem here. Okay, so say the question is determine the contribution to Helmholtz a free energy kilojoules per mole, okay, from the translational mode at 500 Kelvin and 2 bar for helium, which is monoatomic in nature. So this is the question. Okay, so Helmholtz free energy. Again, if you recall the definition, how it can be written in terms of the transfer function. Okay, so ZTR by N is given as 2 pi nkt by h square 3/2 kt by p. Okay, now ZTR by N is equal to 2 pi m V by 2 AT to the power of 2 divided by H cubed into P. If you now substitute the numbers, see 2 pi 0026 okay, into 1.6 to the power of minus 27 P by 2 1.3807 to the power of minus 23 500. This entire thing is raised to the power of 5 by 2, okay, divided by 6.6 so 34 loop 10 to the power of 5. Okay. So from here we calculate, this actually leads to Z translation by N is equal to 5.808 into 10 to the power of 5. Okay. Then of course, so if you now substitute this, let us substitute it in the expression. Translation is equal to minus, again we are writing it ln z dr by n plus 1. It is equal to minus 13.272 plus 1,000, which gives you minus 14.272. Okay, so we obtain ATR is equal to minus 14.272, 8.3145 joules per kilomole per Kelvin per mole into 500 Kelvin, which will give you the ultimate answer, which is minus 58.333 kilojoules per mole. Okay, so this is one sample problem that where we have shown that this is indeed possible to do this. Now let us look at the final mode, which is the electronic mode. Now the electronic mode requires a direct summation on the relevant term symbols and energy levels, right? So it requires on the relevant term symbols, okay. Requires direct summation relevant term symbols and energy levels, which is basically centimeter inverse. Okay. So this is tabulated in Appendix J of the book. Appendix J. Feel free to go there and check. Okay. In most cases, the first few electronic levels needs to be considered because higher excited levels at typical temperature is almost improbable. So the first few electronic levels only matters. Levels only matter, as higher ones are improbable. Okay, they are improbable because of the high temperature requirement. The high temperature requirements. Okay, so nevertheless, you can establish cutoff on a case-by-case basis at high temperatures. For example, if you consider we consider only 3 electronic levels for gaseous aluminum. For this case, we would normally require only the first 2 levels for calculating the partition function because the huge gap between the second and the third levels. Okay, so if we look at like atomic aluminum, Okay. Okay. So let's look at the term symbol here. And this is TE, which is centimeter inverse. So 2P half. You recall the symbols. 0, 2P 3 by 2 is about 112.1. And 2S half is about 25,347.8. So as you can see that there is a huge gap. There is a huge gap. Okay, only we require the first two levels, because you see the second and the third level, there is a huge gap. Okay, when we calculate the partition function for gaseous aluminum. Okay, so this partition function, therefore, electronic evaluated at 1000 Kelvin. Okay, 1000 Kelvin will be G naught plus G1 to the power of E1 by KT, which is equal to 2 plus 4, okay, plus 4 exponential minus 1.4387 into 112.1 divided by 1000 Kelvin. Okay. So this gives you a number which is 5.4042. Okay. So contribution from any energy mode to properties like internal energy and heat capacity is basically comes through T dln z by dt at constant V, and dt the partial with respect to t. So you always need these quantities, right, to calculate the salient features. For the electronic case, contributions of these two expressions can be derived on the term by term differentiation of the partition function at for the electronic levels. Okay, so the algebra is like this. Therefore, let's write it. ZL. Okay, and T partial with respect to T square. dt by ZEL minus ZEL. This is the primary differentiation. And first differential. Okay, where we write ZEL is basically, sorry, it's not the differentiation, it's just we'll write the expressions. You will see that in a bit. It's differentiation, but not in the form. We'll just write it in a second. So ZEL prime is equal to J. So this is the differentiation. First one. Okay. And then, of course, we differentiate it again. Okay. So this provides you, this is a very long, tedious differentiation process, as we can see here. So this is you differentiate it once, okay, and then you, with respect to t, and then you differentiate it another time. So the second derivative. So immediately preceding expressions provides now the required tools for evaluating the contributions of the different thermodynamic properties for an ideal monoatomic gas, right? So U by RT EL is equal to H by RT EL the first differential, the first derivative, and then CV by R L is equal to CP by R L is equal to the second derivative square. Okay. Similarly, we can obtain for S by R L plus ln ZL. Okay, so now if you have to calculate the specific heat, so these are the expressions. Now if the problem is that calculate specific heat at constant volume, which is J by K mole, okay, for nitrogen, okay, at 3000 Kelvin. Okay, so the contribution for the specific heat for a constant volume CV by R TR, the translational mode, is only 3 by 2. You know already. Now the electronic mode, which is CV by R electronic, which is given as ZEL double prime ZEL minus ZEL divided by ZEL. Okay, so this can be done. The electronic contribution can be easily determined by the setting up the table. We can set up a table and then we can compute all the quantities from there. Okay, so like we did in the last time, this is EJ, the GJ, EJ by KT. This is a tabulated form. So this is GJ into exponential EJ by KT. Then it is GJ EJ by KT into exponential minus EJ by KT, then so on and so forth. So you understand how each other, so these quantities are given. So I'm just going to compile a few. So it is 0, GJ is equal to 4, EJ by KT is equal to 0. So this becomes 4, this becomes 0, and the next one is also 0. Okay, so the next energy level 2 to 9, okay, 2 to 9 is therefore given as, this is 10, this is 9.2216, this is 9.880 into 10 to the power minus 4, this is 9.1183 into 10 to the power minus 3, and so on and so forth. So similarly, you can tabulate these three. So if we consider the first 3 electronic energy levels of nitrogen is also given in appendix J.1, the energy corresponding to the fourth is very high. So for nitrogen, so for a given thermodynamic temperature of about 3000 Kelvin, it doesn't really matter. So maybe for your convenience, I'll write this also. 630 830. This is 5.9137 into 10 to the power of minus 6. This is 8.1787 into 10 to the power minus 5. Okay. So the final row of the table, you sum up all these quantities, right? You sum up and then you find out. So you sum up across these levels because that is what is required. So your CV by R for electronic will be equal to, once again, let us write it, electronic. You know the definitions now, each one of these terms. So it is 8.51217 to the power of minus 2 divided by 4.0010 minus 9.2001 into 10 to the power of minus 3, 4.0010 squared. So this is actually 0.02129. Okay. So the summing up the traditional things, if you now do the complete summation, which is basically CV by R, is CV by R translational plus CV by R electronic. So this gives you 1.5000 plus 0.0213, which is 1.5213. Okay, therefore CV becomes 12.649 joules per kilomole. Okay, so this is the standard argument now. So we have done a couple of problems to show. For diatomic gases, the evaluation of the thermodynamic properties for diatomic gases requires that you take consideration of now the rotational and the vibrational modes as well as translational and electronic modes. Right? For diatomic case, complete mode separation, again, if you recall, it requires a simplex model and the combined rigid rotor and the harmonic oscillator type model. So using this model, the property calculations can be straightforward. We only need to sum the relevant contributions. In particular, the separate contributions from the rotational and the vibrational modes are merely added to the translational and the electronic modes. So that is what we are going to do in this. So for diatomic gases, okay, so for diatomic gases, we have a slightly, as we said already, so this is what we are going to do. We are simply going to add, right, for the two. So the translational mode of a diatomic the translational partition function is based on the conversion to center of mass coordinates that we already know. So ZTR there is 2 pi mkt by h squared 3 by 2 into v, where m is equal to m1 plus m2. So this is the center of mass based coordinate system, which we already did. Coordinate system. Now the total mass represents both the nuclei of the chosen diatomic molecule as well. Okay. For the electronic mode, we observe upper energy levels of diatomics tends to be substantially higher than the ground and electronic level. So upper electronic levels of diatomics tend to be a lot higher. Okay, tend to be substantially higher than the ground electronic level. Okay, so therefore your partition function for the electronic level is J e exponential Ej by kt will almost reduce to G naught, which is the ground. Because however, there are exceptions like oxygen and nitric oxide, for example, which are actually this is not quite correct. So any substantial electronic contribution demands adherence to the consistent zero of energy, which we already discussed, which we will discuss now. So in the following section, but so the zero of energy for a diatomic molecule can be set either at the minimum of the Morse potential, defining the ground electronic state, or at the ground vibrational state with this particular Morse potential. So if you look at this, if this is your Morse potential, you can set this or you can set this. So this is the zero. This is the zero. Minimum of the, this is the minimum of the Morse potential for the ground electronic state, whereas this is the vibrational zero, okay, for the ground electronic state. Okay, so another possibility is to set the zero at the ground electronic state correspond to those atoms produced by dissociation. This, of course, requires that we define a dissociation energy as well as a binding energy. Okay, so there are varieties of things that we then need to do for doing this. So let us, if we draw this diagram properly, let us see the possibilities. So this is one. This is the other one. Okay, so this is your first This is ground vibrational. This is T naught. Okay. Then this is your TE. Okay. You can also define something like a dissociation. So that means if you pull these things back a little bit. So this particular thing is your DO. Okay. And this is your DE. Okay. You understand what DE and dissociations are. So dissociation energy is DO. Okay. Binding energy is DE. Okay. So as we showed in this particular figure. So there are various possibilities, therefore, for establishing what we call the zero of energy. There are various possibilities to, establish the zero of energies, and we can compile all of them in a table and define the internal energy for any diatomic molecule. Okay, so this is required because why this is required? Because we have to discuss that how the rotational and the vibrational bands comes into the picture. So the zero of energy is the data is actually very important. So in the next lecture, we are going to finish this off. We are going to see that how this can be done, okay, for how to establish the zero of energy and what are the different possibilities. So we're going to look at a table. We're going to basically compile a table, and therefore then we can start to define the rotation and the vibrations accordingly.